Last time we saw how we can use calculus to help compute some expectations of random variables that depend on a real parameter. But maybe we can use calculus more directly. After all, expectations are integrals, and integrals are half of what calculus is about, the other half being derivatives. Now that's only on the real line, so let's focus our attention on the real line. We have spent the last several weeks developing the theory of integration with respect to general measures, and in particular with respect to the Lebesgue measure on the real line. Part of the motivation for doing so was that there are certain kinds of functions that are fairly simple, in fact actually simple by our technical definition, which were not integrable using the old-fashioned way to do it via Riemann and Lebesgue. For example, we considered this function, the indicator function of the rationals on a compact interval. That function is not Riemann integrable. The upper and lower integrals will always disagree by the same amount, 1, no matter how fine we take the mesh of a partition. However, this is the quintessential Lebesgue integrable function with respect to any Borel measure. After all, the set that we are indicating by this indicator function is the rationals intersected with an interval, and that is a Borel set. And therefore, this is a measurable function. Not only is it measurable, but it is in L1. And what is its integral? The integral of f d lambda. That's the integral of an indicator function against a measure. We know that that just means we're calculating the measure of that set. That is a countable set, and we know that the Lebesgue measure charges any countable set with measure 0. So this function, which was the essential example of a non-Riemann integrable function, is the simplest function out there to Lebesgue integrate. Great. So we can integrate non-Riemann integrable things now. And actually, here we were dealing with a Borel measurable function, but we could just as well have worked with functions that are measurable with respect to a larger sigma field, like the completion of the Borel sigma field, and we would have had no trouble with a similar kind of indicator function anyway. But the question remains, what if the function that we had is actually Riemann integrable? Then we know how to integrate it the old-fashioned way, but we also know how to integrate it the new-fashioned way, if that Riemann integrable function is measurable anyway. But that sets up a potential conflict. Maybe we have two different kinds of integrals. Let's see what happens. Well, it turns out that there is no conflict, there is no contested election here. If a function is the kind of function we could even attempt to Riemann integrate, that is, a bounded function defined on a compact interval, then it's Riemann integrable if and only if it's a nice function from the perspective of the Lebesgue integral. Here's the theorem. Again, let's denote the completion of the Borel sigma field as B bar with respect to the Lebesgue measure. And remember, we developed at least two different kinds of completions. Completion with respect to the pseudometric, completion with respect to null sets, and we alluded to a third kind of completion, which was the Caratiadori criterion completion. As commented before, all three of those lead to the same sigma field. So that's what we mean by the completion here. The Lebesgue sigma field is what it's sometimes called. Then, if you start with a bounded function on a compact interval, it is Riemann integrable on that interval if and only if it is measurable with respect to the completion of the Borel sigma field and the Borel sigma field in the range. And it is continuous almost everywhere, meaning exactly that the Lebesgue measure of its set of discontinuities is 0. And here's where it's critical that we deal with the Lebesgue sigma field, because Riemann integrable functions need not be Borel measurable. The set of discontinuities of a Riemann integrable function can be a subset of a Borel set of measure 0 that is not itself a Borel set. But provided that we are in that extended sigma field, and we do have almost everywhere continuity for our function. Therefore, it will be Riemann integrable. Vice versa, if it's Riemann integrable, its set of discontinuities will have measure 0. And in those cases, here's the critical point, the Lebesgue integral of that function will exist and is equal to the Riemann integral of that function. Now, I'm not going to prove all of this. It is in the notes here if you'd like to see how the full proof proceeds. What I'm most interested in from this proof is this statement here. The point being that if a function is Riemann integrable, then the Riemann and the Lebesgue integrals actually agree in the context where we can define the Riemann integral for a bounded function on a compact interval. So let's see why that's true. Suppose that our function is Riemann integrable. Okay, well, what does that mean? That means that its upper and lower integrals over partitions get closer and closer together as the partitions are taken to have finer and finer mesh. So in particular, what it means is that for any tolerance epsilon, we can find a partition, pi, which we'll write as usual as some partition points t0, t1, up to tn on the interval from a up to b, such that the thing which we know actually agrees, the upper and lower integrals, which is the Riemann integral, which we'll call integral of f at x dx, is less than or equal to the lower integral over pi plus epsilon, okay, and greater than or equal to the upper integral over pi minus epsilon. After all, this is the supremum of these things, which is exactly to say that for any epsilon, we can find a pi so that this is true. And similarly, this is the infimum of those things, which gives us this lower inequality. Now, that's using the terminology from the Riemann integral, but it actually connects very well with the terminology from the Lebesgue integral. In this partition here, let's denote the intervals from tj minus 1 up to tj as ij, and the length of that interval, for the sake of notation I'll call the absolute value of the interval, is of course tj minus 1. Well, this lower integral is exactly defined to be the sum, j going from 1 up to n, of the infimum of f on the interval ij times the length of ij. But we can write that as a Lebesgue integral of a simple function. If I define phi lower sub pi to be the simple function which takes values infimum on ij of f on the interval ij, then this sum is nothing other than the Lebesgue integral of phi lower pi d lambda, simply because the length of the interval is indeed lambda, measure of that interval. And so, by noting now that this phi pi is defined to be the infimum of the function on some intervals, that means that it's less than or equal to the function everywhere. So that phi lower pi is a lower bounding, simple, measurable function. Those intervals are Borel measurable. And so by the order property for Lebesgue integrals, this thing here, which is now a Lebesgue integral of phi pi, is less than or equal to the Lebesgue integral of f plus epsilon. Now, an entirely analogous argument, by constructing a phi upper pi to be the simple function which takes values supremum on ij of f on the interval ij, well, that means that this thing, the upper integral, is the Lebesgue integral of phi upper pi d lambda. And now by the same idea, the order property of the Lebesgue integral, that is going to be greater than or equal to the integral of f d lambda, because phi upper pi as a function is greater than or equal to f everywhere. And so that means that we have the inequality over here that this is greater than or equal to the Lebesgue integral of f d lambda minus epsilon. So now, putting those together and noting that we've lost the partition, we see that for any epsilon, the Riemann integral sits in between the Lebesgue integral minus epsilon and the Lebesgue integral plus epsilon. It therefore follows that by taking epsilon down to 0, the Riemann integral is equal to the Lebesgue integral, as claimed. Now, as for the other statements about characterizing those functions that are Riemann integrable, being those that are appropriately measurable and are continuous almost everywhere, let's just note that if the function f were continuous, then we could also easily prove that either of these functions, f lower pi or f upper pi, actually converges everywhere to the function f. And then by using the monotone convergence theorem over here, or the dominated convergence theorem in greater generality, we would be able to conclude what we want to conclude, that in fact the function is measurable in the appropriate sense. Now that was assuming continuity, so this doesn't come into play. If we want to deal with discontinuous functions and conclude how continuous they are, we need to be a little more clever about how we approach this. And I'm not going to get into this right now. We will use this theorem largely in the case where the functions in question are actually continuous. Now the Lebesgue integral also allows us to handle so-called improper integrals of Riemann type. For example, we'll frequently, from calculus, try to compute things like this: the integral of some function that will decay near 0 fast enough over the whole real line from minus infinity up to infinity. Now, in the case of Riemann integrals, that is not definable as a Riemann sum type limit. The Riemann, Stieltjes, Darboux approach to integration fundamentally only works for bounded functions on compact intervals. And so we then define an integral like this after the fact as an improper integral, which means taking a limit, as say n goes to infinity, of the integral on the compact interval from minus n up to n. Well, in fact, the Lebesgue integral can come to our rescue here and define this without the use of a limit. Let's limit ourselves to the case where the function in question is non-negative. That will be enough for anything we're going to need to use this for. Now, this limit, let's note, can be written as a limit of Lebesgue integrals by what we just wrote. Let's suppose that our function is Riemann integrable on each interval from minus n up to n. Then, as we just saw, that means it is equal to the Lebesgue integral on that compact interval of f, which we'll rewrite one more way, just remembering what it means to integrate over a Borel set is just to integrate the function against the indicator function of that Borel set. And now let's note the following. The indicator of the interval from minus n up to n as a function at each point is less than or equal to the integral from minus n minus 1 up to n plus 1. But because we're assuming that the function f is non-negative, that means we can multiply through that non-negative valued function to get that f times this indicator is less than or equal to f times this indicator. And now we've set ourselves up nicely for the monotone convergence theorem. Because I now have a sequence of non-negative measurable functions inside here that are increasing, and therefore by the monotone convergence theorem, the limit of their integrals will be equal to the Lebesgue integral of their limit. But of course, pointwise, this limit, at least in the case where the function is continuous, let's say, will equal f. Now, of course, we know we only need that limit to be an almost everywhere limit, so for this statement, it's good enough to assume that f is continuous almost everywhere, and then we'll still get that this limit inside is equal to f on a set of full measure, which is all we need. So in other words, the conclusion is that if I have a almost everywhere continuous non-negative function f, its improper integral in the Riemann sense is just equal to its Lebesgue integral. And therefore, we have that such an improper integral is finite if and only if that function is actually in L1 of Lebesgue measure. There's some notation, by the way. If it's clear from context that the space is the real line and the sigma field is the Borel sigma field, we can just indicate which measure we're using if that's in doubt, instead of writing RB lambda. Now we could also handle improper integrals of vertical asymptote type in a similar way, and I'll leave that to your imagination. Everything we just discussed was for the Lebesgue integral with respect to Lebesgue measure on the real line. But there are certainly other measures on the real line that we'll need to contend with. What about other Borel measures? Now, there is a nice fact that we have that as long as our Borel measures are finite on every compact interval, and that'll certainly be true for probability measures that are finite on the whole real line, then we have a characterization of them as Radon measures, that is, measures that are determined by a non-decreasing right continuous function f by this formula. Now, let's take a special case here, but an important special case. We know that the function f in question will be right continuous and non-decreasing, but maybe it's more. Maybe it's continuous, and even better, maybe it's differentiable, and even better still, maybe it's continuously differentiable. So let's suppose for the moment that this function is continuously differentiable everywhere on the real line. The reason I want to make that assumption is that now we can go back to calculus and apply the fundamental theorem of calculus, which says that in this case, the measure of the interval from a up to b, the half-open interval as usual, which is f at b minus f at a, by the fundamental theorem of calculus, that can be calculated as the integral, Riemann or Lebesgue now, we know, over the interval from a up to b of the derivative of our function. Okay, and so I'll write that again explicitly as alternatively the integral over the interval from a up to b of f prime d lambda. Now, on your homework, you explored measures that can be written in this form, where the measure of a set is the integral of some function over that set. In that homework problem, we needed to assume, for this to be a measure, that the function you're integrating against is a non-negative measurable function. Well, the function f prime is non-negative because f is increasing. And if f is non-decreasing and differentiable, then its derivative is greater than or equal to 0. Moreover, we assume that the function is continuously differentiable, which means that its derivative f prime is continuous. Continuous functions are Borel measurable, so this is certainly a measurable function. Does this mean that the measure is given by density f prime? Well, for that to be true, we need to check it not just on intervals, but on all Borel sets. That can be hard, but again, we have nice uniqueness theorems about measures. So let's check it more generally and say, define a new measure, nu, on all Borel sets A by the integral over A of this particular non-negative measurable function f against Lebesgue measure. You proved on your homework that this defines a nice measure. Then what we see here is that nu and mu agree on the semi-algebra of half-open intervals. But we know that if I have two genuine measures that agree on a semi-algebra, they must agree on the sigma field generated by that semi-algebra, which is the Borel sigma field. And so indeed, from here, we see that the measure mu is given by integrating the derivative of the function f on any Borel set. And so you can conclude further by your homework problem that if I want to integrate any appropriately integrable function, little f, against this Radon measure mu on the interval from a up to b, you can do that by integrating f times the density f prime d lambda on that interval. Now, we would love that to still be the kind of integral we know how to do from calculus, a Riemann integral. And we will be able to conclude that because from your homework you saw that this is true for any function f that is in L1 of the measure mu, which we're restricting for our purposes right now to the interval from a up to b. and that condition is satisfied if and only if the absolute value of f times f prime is in L1 of Lebesgue measure. Well, f prime is a continuous function here, and so if little f is Riemann integrable, it's easy to check that this is therefore also Riemann integrable. And so we can write this as the Riemann integral from a up to b of f at x times f prime at x dx. Thus, we see that radon measures in the case where the cumulative distribution function f is continuously differentiable actually have a continuous density with respect to Lebesgue measure, and we can then compute integrals with respect to any of those measures as Riemann integrals. Now, how general is that? Does capital F need to be C1 in order for that to work? Not quite, but it's pretty easy to see that it's not going to work in great generality. For example, consider point masses, which are, of course, radon measures. The point mass at x is the radon measure with cumulative distribution function f given by an indicator function of the set bigger than x. Of course, we know what that means. It means that the measure of any Borel set, or actually any subset of the real line, is equal to 1 if x is in that set, and 0 if it is not. Now, suppose we wanted that measure to have a density with respect to Lebesgue measure. Suppose we wanted to be able to write that as the integral over A of rho d lambda for any set A, that is, say, Borel measurable, where lambda makes sense. Let's see if we can suss out what that density function rho ought to look like. Well, if I take any half-open interval from A up to B, and it doesn't contain the point x, then that means that the integral over that interval of rho must be 0. But the rho, being a density, must be non-negative. And if I have a non-negative measurable function whose integral is 0, then as we proved, that implies that rho is equal to 0 almost everywhere with respect to the Lebesgue measure on that interval from A up to B. Now that was true for any interval that doesn't contain x. So we're therefore going to be able to conclude that rho is equal to 0 almost everywhere with respect to Lebesgue measure on the whole real line with x removed, just by taking intervals closer and closer to having that point removed. But that point has Lebesgue measure 0, so being almost everywhere 0 on the reals minus x is the same as being 0 almost everywhere on the real line. And we know that if a function is 0 almost everywhere on the real line, then its integral over the whole real line, and therefore over any Borel set, will be 0. Which means that we cannot capture that 1 if x is in the set this way. So there can be no density for a point mass, or therefore any convex combination of point masses. If a radon measure has any point mass anywhere, it cannot have a density. So in other words, if we want there to be any chance of having a density, the cumulative distribution function must be a continuous function, which is the same as saying that there are no point masses anywhere. This is the distinction usually drawn in undergraduate probability courses. But it's not good enough, of course, for f to just be continuous. If we want to mimic the calculations on the previous slide to find a density from a continuous cumulative distribution function f, it has to be continuously differentiable. Well, maybe it doesn't actually have to be completely continuously differentiable, but we at least need it to be close enough that the fundamental theorem of calculus holds. To be precise, if I have a cumulative distribution function f that is differentiable almost everywhere, and nice enough that integrating the derivative recovers the original function, then we can mimic the calculations we did a few slides ago to see that the measure that has that CDF has density f prime. Just being continuous and differentiable almost everywhere, however, does not guarantee that the fundamental theorem of calculus holds almost everywhere. And the classic example of that is the weird example we already saw, the devil's staircase, which is a function that is flat everywhere on the complement of the Cantor set, but is continuous and rises from height 0 up to height 1 on the unit interval. The Cantor set has Lebesgue measure 0, so that means that this function is differentiable almost everywhere, and its derivative is 0 on the points where it's differentiable, because the points where it's differentiable at least contains the complement of the Cantor set, where its derivative will be 0. However, it certainly does not satisfy the fundamental theorem of calculus, because the integral over the interval from 0 up to x of f prime d lambda is the integral of 0 almost everywhere, which is just 0. And that's not f at x for any x bigger than 0. So the fundamental theorem of calculus doesn't apply to this continuous, almost everywhere differentiable function, and therefore the Radon measure with this CDF does not have a density. The thing that went wrong here is that while this function f is continuous, it is not what is called absolutely continuous. Now, we're not going to get into the details here. The fundamental theorem of calculus will hold for functions f that are absolutely continuous, and this is the prime example of one that is not. You can look up that definition if you want. I just want you to be wary going forward that densities aren't always around in the mix, even when cumulative distribution functions are very continuous. So now we have some ideas of how to actually calculate some integrals and therefore some expectations. Well, that is, only if those expectations can be computed as integrals against Lebesgue measure or particularly nice Radon measures on the real line. But our expectations are usually integrals with respect to some abstract probability measure, not a Radon measure on the real line, right? Well, stay tuned.